Welcome back. So we're going to do section 4.4, and then we break for a test. It'll be one of the 2 tests out of the 9 weeks. We will take that test by the end of next week. Sound good? By the end of next week, we will do the 4.1 to 4.4 test. That'll be Thursday, Friday of next week. Section 4.4, I will probably be able to teach today and tomorrow. That leaves Friday as a work day. Monday, I will give you the test review. You'll work on it. Depends on how we do on Monday, how we feel on Monday. I can start going over questions on Tuesday. Tuesday, Wednesday, we'll review, and then test Thursday, Friday of next week. Does that sound good? Okay. All right. Section 4.4 is called Indeterminate Forms, and you pronounce this guy's name L'Hopital. L'Hopital's rule. Okay, so take a look at this function. Okay, take a look at that function. ln of x over x minus 1. And I wanted to study the behavior of that function, meaning like I want to figure out what it's going to look like. Well, I want to figure out what it's going to graph like. What point is really weird on this function? What point is undefined on this function? 1, right? There's this really weird point happening at 1 that is undefined, and something weird we know based on our previous knowledge of these functions, this rational one, it's undefined at 1. So that means like it could be a vertical asymptote, it could be a hole, it could be something weird happening. Okay, we just don't know what is happening at that moment. Okay, now, although f is not defined when x equals 1, we need to know how f behaves near 1. We need to know what's going on around 1. In particular, we would really like to know the value of that limit. We would really like to know what's happening as x approaches 1. The limit as x goes to 1 of this thing. Now, think about this. If I were to do direct substitution, you'd say, well, you can't do that because the denominator goes to 0. Yes, that's true. You're right. But it goes to 0 in a unique way. Think about it in terms of how it relates to the numerator. If I plugged in 1 to the numerator, what is ln of 1? If I plugged it into the numerator, what is ln of 1? Oh, it's also 0. It's also 0. Actually, if I plug in 1, I get this weird thing where it goes 0 over 0. So you would say, well, yeah, that's still undefined. Yes, it is undefined, but it's undefined in a unique way. It's what's called an indeterminate form. An indeterminate form. Sorry, I always say that wrong. I always say indeterminate, like there's another N there. Indeterminate form. It's an indeterminate form of 0 over 0. Whenever you have this case where you plug it in and you get a 0 over a 0, there are other indeterminate forms. If you plug it in and you get a 0 over a 0, something weird is happening. You kind of have to investigate it further. It's like a sign in your head going, okay, watch out there. Red lights are going off. Something weird is happening. In computing this limit, we can't apply law of 5 limits plugging it in because the limit of the denominator is 0. In fact, although the limit exists, its value is not obvious because both numerator and denominator approach 0, and 0 over 0 is undefined. So this is what's called an indeterminate form of the type 0 over 0. We've seen this before, okay? We've worked with this before. We worked with this back in chapter 2 when we were studying limits. Take a look at this limit right here. Take a look at this limit. We found our ways around it earlier. The limit as x approaches 1 of x squared minus x over x squared minus 1. At the very beginning of in chapter 2, we said, well, we can't do that, but what we can do is factor that thing down to make 1 cancel out, right? We can factor that thing down to make 1 cancel out. I factor out the x in the numerator. I factor down the denominator. I'm able to cancel out an x minus 1, leaving an x over x plus 1, which puts it to 1/2. So we found our ways around that. But can I factor down this? Can I do that algebraically with this? No. Okay, take a look here. What's the derivative of the numerator? 2x minus 1, right? That's a really simple derivative. What's the derivative of the denominator? Just 2x. What's the limit as x approaches 1 of this thing? Can I plug it in now? What do I get? 2 minus 1 is 1 over 2. What? What? This is what L'Hopital said. He quoted, what? So you mean to tell me, it's quoted in his book. So you mean to tell me if I have the derivative, I could possibly plug that in? Yes, that's L'Hopital's rule. That's L'Hopital's rule. Suppose that f and g are differentiable. They have to be differentiable. And the derivative of g does not equal 0. That makes sense because if I go to plug it in, I would get a 0 in the denominator once I take the derivative. On an open interval that contains a, except possibly at a, I don't really care what's happening at a. I know it contains that value though. Suppose that, now, this is saying, okay, this whole chunk is saying you get a 0 over 0 or the other indeterminate form, infinity over infinity. Infinity over infinity. If you get 0 over 0 or infinity over infinity, or in other words, you get an indeterminate form, okay, you have an indeterminate form 0 over 0 or infinity over infinity, then you can apply L'Hopital's rule. If you get an indeterminate form of 0 over 0 or infinity over infinity, you can apply L'Hopital's rule. You have to make sure that the hypothesis is true. Okay, you have to have an indeterminate form. What tends to happen is sometimes you get so caught up in doing L'Hopital's rule, you forget to even check that it's an indeterminate form in the beginning. Okay, it has to be an indeterminate form. It has to be a 0 over 0 or infinity over infinity. Okay, if it's not, then L'Hopital's rule doesn't work. It may work coincidentally in certain times, but it doesn't always work. Now, if you have that case, here's what you can do. As long as you have this rational function where I've got two functions, either numerator and denominator, I can take the derivative of the numerator and the derivative of the denominator and apply the limit to that. I can take the limit of the numerator and the limit of the denominator and apply the limit to that. Some things to note. L'Hopital's rule says that the limit of a quotient of functions is equal to the limit of the quotients of their derivatives, provided that the given conditions are satisfied. It is especially important to verify the conditions. Okay, it's especially important. What am I saying there? It's especially important to make sure that you have an indeterminate form. I cannot stress that enough. You've got to make sure it's an indeterminate form. It's got to be 0 over 0 or infinity over infinity. You can't have 0 over infinity. 0 over infinity would be 0. You can't have infinity over 0. That's undefined. Yeah. Please don't mistake me. If I put 2 over 0, that's not an indeterminate form. That's undefined. Okay? That's not an indeterminate. There are two different things. An indeterminate form is only 0 over 0, infinity over infinity for right now. But for a lot of the times we'll say like, oh, that might be an indeterminate. That's not an indeterminate form. A number over 0 is not an indeterminate form. It's just undefined. L'Hopital's rule is also valid for one-sided limits. I could say A from the left or A from the right, and this whole thing still holds. Okay, it doesn't matter whether you use a one-sided limit or a two-sided limit. Same rules still apply. L'Hopital's rule is also valid for one-sided limits and for limits at infinity or negative infinity. Yeah, I could make that A value like x goes to infinity or x goes to negative infinity. That all works the same way. Okay. Yeah, I don't think we need to worry about part 3 there. Let's take a look at this one that we talked about at the beginning. Find the limit as x goes to 1 of ln of x over x minus 1. Okay, the first thing that I have to do is make sure that this is an indeterminate form. Let's make sure that this is an indeterminate form. We kind of already did that. If I take the limit as x goes to 1 of ln of x, and the limit as x goes to 1 of x minus 1, I need to make sure that these are both 0 or both infinite. We've already seen ln of 1 is 0. We also know that that is also 0. Okay. Show me what type of indeterminate. Whenever you do these problems, make sure you state within the problem what type of indeterminate. Do you have a 0, 0? Do you have an infinite over infinity? So this is indeterminate form 0 over 0. Basically, this is part of the problem where it's saying, okay, we can do L'Hopital's rule. It exists. We can do that. And L'Hopital's rule says that I can find the derivative of the numerator and the derivative of the denominator separately. Now, please don't confuse this with the quotient rule. I know that it is a quotient, but L'Hopital's rule kind of breaks it apart and uses them as two separate functions. I am not using the quotient rule. Okay, so let's take the derivative of the numerator. What is the derivative of ln of x? 1 over x. What's the derivative of x minus 1? 1. Oh, cool. So that just goes to 1 over x. And now I apply the limit back on. The limit of the function is the limit of the derivatives. Now we apply the derivative. Or now we apply the limit, excuse me. So the limit is actually 1. As x approaches 1, it goes to 1. Questions there? Okay, let's take a look at this. All right, calculate the limit as x goes to infinity of e to the x over x squared. Calculate the limit as x goes to infinity of e to the x over x squared. Excuse me. Okay, let's take, first off, can I do direct substitution initially? Well, I guess that's kind of like checking like L'Hopital's rule already, right? Let's find the limit as x goes to infinity of e to the x, separately from the limit as x goes to infinity of x squared. Okay, if I say the limit as x goes to infinity, I'm basically saying on the right side of this graph, right? What's happening on the right side of e to the x? It's going up, right? It's just going to keep getting bigger and bigger and bigger, right? That's what e to the x looks like. So this is going to be infinite. Okay, what is the limit as x goes to infinity of x squared? Well, on the right side of our quadratic, it also goes up. So I know this is infinite as well. So I can say that this is the indeterminate form of infinity over infinity. Now be careful. It's always tempting to say, oh, infinity over infinity 1. No, it's not 1. Because think about this. Is this the same value as it grows? Is e to the x and x squared always giving the same value as they grow? No. E to the x is going to go way faster than x squared, right?
Will it work if like one of them was going at negative infinity?
No. It's got to be positive infinity, or negative infinity, or negative infinity. Good question, though. So on the right side, as I grow, I am not growing equally, right? I am not growing at the same rate. I am growing faster with e to the x than I am to x squared. That's why it's not 1. It's tempting to say 1, but it's not 1. Trust me. Okay. It's an indeterminate form. Okay, so that means all that's saying that I can use L'Hopital's rule. So e to the x over x squared will turn into, well, what is the derivative of e to the x? E to the x. What is the derivative of x squared? 2x. Okay. Well, now let's apply the derivative. Move that over, or not. I keep saying that. Now let's apply the limit. Well, when I apply the limit, take a look and see what happens. What happens to e to the x? Isn't it the exact same thing, right? I can say the limit as x goes to infinity of e to the x. Well, that's still infinity, right? What's the limit as x goes to infinity of 2x? Isn't that just a linear function, right? 2x. What's happening on the right side? It's still going to keep going up. So you may be thinking, oh, we're stuck. Oh, we can't use this. No, we just use it again. Yeah, we just use it again. Can't we do L'Hopital's rule again? This is an indeterminate form again. 0 over, or not 0, 0, infinite over infinite. Okay, so just find the second derivative. Keep it going. There's like an infinite loop of these things that you could possibly do. So we could say, the limit, I need this. E to the x over 2x, right? Find the derivative. Well, what's the derivative again of e to the x? E to the x. What's the derivative of 2x? 2. Right? So now, let's apply the limit now. Oh, don't grab that arrow. Oh, stop that. Oh, geez, Pete, I've really made a mess of things right here. Should have just rewrote it. Okay, so now we say the limit as x goes to infinity of this thing. Well, if I plug in this, e to the x, the limit as x goes to infinity of e to the x is still infinite, right? But is the limit as x approaches infinity of 2 infinite anymore? The limit of the constant is the constant. And even if I'm dividing infinity by 2, isn't it still going to get to infinity? There's my answer. So, moral of the story here is you can keep using L'Hopital's rule. If you keep getting indeterminate forms, you can keep using L'Hopital's rule. Yeah.
If e to x is in the numerator, will the answer always be infinity?
Not necessarily. When would it not? I'm trying to think when it would not. I mean, it could be if you had e to the x over like e to the x minus 2, then you'd be stuck in an infinite loop of L'Hopital's rule, right? And you would never be able to solve it. So it's not always going to be infinite. Yeah, it's not always going to be infinite, but most of the time, yes. Yeah. Questions there? Okay, I promised Miss Hayes and Miss King that we would not move on too far because they're out. So they came to us and they don't go too far in the notes. So I'm going to stop there in the notes, and we will finish up tomorrow. That sound good?